Hello. So we will learn solutions. A very important, a very simple but very important concept that will help you understand solutions better. So it's a law called Roult's law, which has been named after a French chemist in 1886. Roult's the Roult's law. Let's try to understand what does Roult's law say. The Roult's law says that suppose you have a container, right? You have a container and there are two liquids. There are two volatile liquids. So you're mixing two volatile liquids, so it's a solution. Solution is a solution. It means the composition, the concentration of the two liquids. Let's consider a binary solution containing only two components. There may be more than two, but for the sake of simplicity, that there be only two components. So it's a binary solution. So there are two components. I have denoted it with the two colors, blue and green. So for a solution of two volatile liquids, the liquids are volatile. That means they change the liquid state, the molecules in the liquid state, they change to the vapor state, and then from the vapor state, they again change to back to the liquid state. So there's a conversion going on from the liquid state, the molecule from liquid to the gaseous phase, and from the gaseous phase to the liquid phase. So that interconversion goes on, but after some time it attains an equilibrium, so that the number of molecules which is staying in the liquid form and the number of molecules of the same component in the gaseous form becomes constant. Although interchange is going on, but the number becomes constant, so it has attained an equilibrium state, right? At that particular point, right? So there are two liquids. So let's consider the blue ones. So whatever the component of the whatever the molecules of the blue component, that is up. Suppose there are 10 molecules in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 molecules are there. 6 of them are still staying in the liquid form, and 4 of them are above it in the gaseous form. So they are exerting the gaseous forms. That means the molecules in any substance in the gaseous form means its molecules are striking in all the directions. So they are exerting pressure, and that pressure is called vapor pressure, right? This is, although this is a very simple term, but many fail to understand what exactly is vapor pressure. Why don't this just say pressure? Why there's a word vapor in it? So it's called vapor pressure. A liquid in a container, it's at a fixed temperature. The temperature is not changing at all. At that particular moment, the pressure exerted by those those components or those molecules in the gaseous state is known as vapor pressure. It's exerting in all the directions. So I have covered the container. This is container and it's been covered. This the black horizontal line. It resembles, it's a lid over the container. Fine. So the vapor pressure of that component. So since there are two components, instead of saying vapor pressure, let's say, because there are two components, so both the components are exerting pressure. Both the components are having the vapor pressure. So let's say, instead of saying vapor pressure, let's say partial vapor pressure. So partial vapor pressure of one of the components, say the first component is component number one, is proportional. It's proportional to the mole fraction of that component. Component number one. What is mole fraction again? Mole fraction, I have not written it. It's a ratio of the number of moles of that particular component divided by total number of moles of all the components. So that fraction is known as mole fraction. It's nothing but it's a concentration of, in simple words, it's just the concentration of the first component, of component number one. So what is the pressure, the vapor pressure, the partial vapor pressure of a component of a component in a solution is proportional to its mole fraction, or just say concentration, right? It's quite obvious. This is not, so this is known as Roult's law. It's not like a very complicated or very complex statement. It just says that at a particular temperature, considering a solution containing volatile liquids, the partial pressure of each of each component is proportional, not partial pressure. The partial vapor pressure of each component is proportional to its mole fraction. In a similar way, if there are two components, the green one denotes the second component. And similarly, the partial vapor pressure of the second component, component number 2, is also proportional to its mole fraction. What is its mole fraction? Whatever it is proportional to its mole fraction. So this particular statement. This is what we call Roult's law. If you understand it, it's very easy, and if you don't, you cannot answer the questions or its applications wherever there is Roult's law. It has a very great use and application in learning the colligative properties of the solution. That is in the last part of the lesson solution, of the unit solution. The colligative properties, the relative lowering of vapor pressure, the elevation of boiling point of the solution, the osmotic pressure, the depression and freezing point. Those are colligative properties which depend on not on the quality or the property of the solid, but depends on the number of the particles of solid that are dissolving in a solution. Those properties are called colligative properties. So going mathematical, if you replace the proportional sign, it's obvious that you will put one constant, and this constant is related to that particular component of the liquid, the volatile liquid. And what is this? This is the vapor pressure, not partial vapor. This is the vapor pressure of that particular component or that particular liquid at that temperature. All right, it means this is the vapor pressure of the liquid of the pure liquid when it's alone. Suppose there are only blue components, no green components are there. So when it is alone at that particular temperature, its vapor pressure, this is that value, the vapor pressure of the pure liquid into the mole fraction, right? Similarly, for component 2 also, when you replace the proportionality sign by equal to, you need to write one constant, and this is what? This is the vapor pressure of the pure component number 2 when it is alone at that temperature. Fine. But what happens when in these two components, suppose the second component, suppose the green particles, they are non-volatile, right? So it will not stay here, it will stay here, the green component. It's in a smaller quantity, so it is solid, right? There are only 1, 2, 3, 4, 5 components are there, and there are 10 components of X. The one which is in more quantity, that is solvent, and which is in lesser quantity is not a solid. That is a general definition we know. And in that case, and if the second, the one here, the green component is in lesser quantity, so it is solid. And if it is a non-volatile solid, that means it won't change to vapor state. It will stay in the liquid state only. Then this will be here inside here, and this particular component can be completely ignored. Only this will sustain. This will remain. So if solutions contains non-volatile liquid solid, then we will ignore this part. And we will say that if there is a solution containing a non-volatile solid, the vapor pressure, we can say, of the solution, or the partial vapor pressure of the, there is no need to say partial vapor pressure, because the only one part will be giving the vapor pressure. So we'll say the vapor pressure of the solution is probably proportional to the mole fraction of that component, or it is equal to constant multiplied by mole fraction. And this constant is what? This is the vapor pressure of that component 1 when it is in its pure state, when no one is there, when he is alone. So when this is ignored, instead of saying partial vapor pressure, we'll say just vapor pressure of what? Of solution. The vapor pressure of the solution is proportional to the mole fraction of the first component of the solvent. I hope you understand this. Now coming to the next one, what is Dalton's law? It is somewhat a derivation of it. Dalton's law of partial pressure. What does it say? It says that suppose there are only two components, maybe there may be two or more than two components, whatever it is. Suppose there are some liquid and they are all volatile, and we have made a solution. So what will be the total pressure above this liquid? What is the total pressure of all the components of the gaseous components? It will be what? It will be the partial pressure of whatever component. Suppose there are two components, so partial pressure of the first component plus the partial pressure of the two components. If there are three, then plus partial pressure of the three components. Whatever components are there, what will the total pressure? What will the total pressure of this or the system? The total pressure of the system of all kinds of the components that are present in the solution it will be equal to sum of the partial pressure of the individual component. This is what the Dalton's law of partial pressure says. It's again a very simple statement. The Dalton's law of partial pressure states that the total pressure the total vapor pressure of a solution containing many components is equal to sum of the individual partial pressure of each component at that particular temperature. Again, now if we apply the Roult's law over here, so this particular statement, this mathematical statement, this is what the Dalton's law of partial pressure says, right? The Dalton's law of partial pressure says that in a solution of volatile liquids, the total pressure or total vapor pressure of the whole system will be equal to sum of the partial pressures of the individual components, right? So if we apply Roult's law over here, what is partial pressure? It is again the product of the vapor pressure for the first component, and when it is alone, when it is pure, multiplied by the mole fraction. Similarly, for the partial pressure or vapor pressure of the second component equal to vapor pressure of that component when it is in a pure form, multiplied by its mole fraction, right? Now, if there are only two components, right? If there are two components, then the sum of the mole fraction will be equal to 1. This is another concept. If there were three components, then x1 plus x2 plus x3 equal to 1. But since there is only two components, we are considering binary solutions. So x1 plus x2 is equal to 1. Fine. So replacing x1 by x2 becomes x1 equal to what? 1 minus x2. So simplifying this, what we get is the total pressure of the system of solution of volatile liquids is equal to partial pressure of the first component, vapor pressure of the first component in its pure form minus